right, this is the second half of Physics 1B for October 6th, and the last thing we did was to find the temperature in this problem. What we need to now do is to find the total heat flow rate through the bars. So that means we need to calculate what H is. And this is probably the easiest one to use. So what we'll do is we're going to take that, which we know is the heat flow through the copper. We'll come down here, and we're just going to calculate what it's equal to. They both should be equal, so either one that we calculate, we should get the same answer. So for the heat flow of the copper, we're going to use the copper conductivity coefficient, which is this one, 385 watts per meter Kelvin. So that's, put that there. And then we're going to multiply that by the cross-sectional area, which we calculated earlier to be 0.004 meters squared. And then we multiply by the temperature. We calculated that. Now we said this doesn't work. We calculated that to be 20.7. So it's now going to be 20.7 degrees Celsius minus 0 degrees Celsius, which now that we know it's a temperature difference, it's pretty clear that we can cancel that with the Kelvin. And then I think the length of the copper was 0.2, right? Yeah. Length of the copper down here was 0.20 meters. And if we calculate that, we're going to get the heat flow. Just bang that out real fast. Come on. Oh my god, why is it doing this? 385 times 0.004 times 20.7, and then divide by 0.2. I bet we could have done this in our heads. 160 is what I get, approximately. 159.4 watts. So that is the heat current through the bar, and you should be able to prove for yourself if you want to that if you did the same calculation using this, that you will get the same answer. And if you don't, it means there must be some error somewhere. In fact, if they're not equal, that means that you probably did part A wrong. So it's always nice to have a way to check your answers. Okay. All right, I should leave it there for a second. Any questions?
All good, all good.
All right, so the next thing we want to talk about is not this stuff, but convection. So let's make some room. I see now that we're past 7 o'clock, my screen has turned yellowish. I don't know if that shows up on your all's end. It doesn't look like it does.
Yeah, it's the night mode.
Night mode. You guys do see that? That's interesting.
Yeah,
That's interesting.
you can turn it off if you go to like the window.
No, I know how to turn it off. I don't really want to.
Okay.
It's nice.
It's like the blue light filter.
Right. Which it's kind of nice on your eyes. Makes the screen seem less bright, so you're not, yeah. I like it. Okay. Convection. So conduction was heat transfer due to contact. Convection is heat transfer due to motion or movement of substance or mass. So, heat transfer due to a movement of substance or matter. So, let me give you a couple of examples of how this occurs. Okay. So, one example that's probably the easiest to discuss is suppose that you have, I know we always use water as an example, but it's the thing we have the most experience with. Suppose that I have some boiling water, okay? And, down at the bottom here, I've got some kind of a flame. Maybe like it's on a stove or something like that. So we've got a stove here, stovetop. And we're heating up this water, right? And so this is heat going in this way. Now, the pot itself that this is held in, like a stock pot or something, it's going to start to get hot here on the bottom, right? Without a doubt. In fact, it'll be hot all around. Every place that you touch here is going to be hot. And of course, that means that the water that's next to it is going to get hot due to conduction. So heat will conduct from the bottom into the water. Now, the water molecules that are down here are going to get really hot, right? And what do you think they're going to do when they get hot? What would you guess?
Rise.
Rise. Yeah, because one thing we all kind of know is that heat rises. And I'm not going to write that down because it's kind of unscientific, but it kind of gets to the point. We all kind of understand that hot objects tend to move upwards because they have more kinetic energy. And if something has more kinetic energy, it can go higher to higher potential energies, basically, right? So these hot water molecules are going to start to kind of move their way up to the top of the fluid, like this. The hot water is going to kind of move up like this. And now, that is going to push down the colder molecules that are up here, right? They're going to be pushed back down here due to that kind of flow of the water. And what you're going to get is an overall circulation that occurs in the water like this. And that circulation is what we call convection. As the hot water moves up to replace the cold water gets pushed down. Those cold water molecules now get heated up by the heat on the bottom. They get pushed to the top, and that process just continues. And the effect is that the water will warm evenly now, right? So it's not just the water on the bottom that's going to be hot, but the entire pot will be warm. All of the water will be warm. And not only that, but it will heat up much more quickly than if you didn't have this process occurring. Of course, you can't stop it from occurring. It's going to happen. This natural kind of, we call this a convection current. Because it's a heat current, you know. And it's mostly because the water that's hot in the bottom rises up, the cold water at the top falls down, and eventually it leads to, you know, even heating. Now, that's not to say that the stuff down here at the bottom isn't going to get really hot. If you've ever made any type of a sauce in a big pot like this, or if you've made like soup in a big pot like this, you might know that if anything gets stuck down here at the bottom, let's say you've got some potatoes and some meat and some vegetables that are kind of stuck down here at the bottom, those things, they can't move up in the same way water can, right? So you can burn stuff if it's in your pot, right? Because we're just talking about what's happening to the water here. And so that's why, of course, you have to like stir these big, if you're making a big stew or something like that, right? You got to stir it to make sure stuff doesn't get caught down on the bottom, because then if it gets caught on the bottom, it's being heated with conduction heat, and that conduction heat is going to be way hotter, which means it's going to be more likely to burn like your meats and your vegetables and stuff like that, or overcook them so they become soggy and not very appetizing, right? Do y'all know what I'm talking about? Have you all experienced that before? Where if you like leave a pot up for a long time, you might burn the bottom?
Yeah, especially with pasta.
Pasta, perfect. That happens to me all the time, right? If I make some like marinara sauce or whatever, and then, you know, on the very bottom, the marinara sauce can get stuck to the bottom, and then it'll heat up really hot, and so that's why you got to stir it a bunch. But as long as you stir it a bunch, then everything will get heated pretty evenly due to these convection currents. Okay, does that make sense about what's going on there with that convection current? Let me give you one other example. So let's say you have a house. Let's not use red, because we'll use red to... let's say you have a house. So here's your house. You got a big, open, drafty room in your house. And let's say this is the basement down here. Okay, so this is the basement. And let's say that in your basement you have a radiator. So here we're going to have a radiator, which is just basically it's a heater, okay? And let's say there's a vent right here, where the hot air right here is going to basically come up. So this is a vent. So what's going to happen is that hot air is going to be pumped from the radiator, similar to the radiator is like this hot thing right here. So the radiator gets really hot, and then a fan will blow air in this direction here which will force it up into the room. So you'll have hot air coming in here, coming in from the radiator, right? Over on the other side of your room is going to be an intake vent. So this over here is going to be an intake vent. And what's going to happen? Well, that hot air is what's it going to do? You all know what it's going to do, right? What's it going to do?
The hot air is going to rise to the fan. The fan's going to cool it off. Then it's going to fall into the intake vent.
That's right. So the hot air is going to rise up. It's going to rise up. But now, guess what? It's really far away from the radiator, so it starts to cool. So what was formerly hot air is now cool. And, it's going to now fall back down because it's cold air, right? Okay, so it cools. And now we have cold air. Cold air is going to flow back into here, into the intake vent, back into your basement, where it might be carried along some pipes or something like that, until eventually it makes its way back over here to your radiator. And when it does, what's the radiator going to do? It's going to heat it up, and then it's going to pump it back into the room. And now we again get a convection current. And the convection current looks something like this. And the effect is that you don't need to sit right next to the vent in order to feel hot. Given enough time, that convection current flowing, the whole room will be warm, and then the radiator will kick off, right? It'll turn off because now the whole room's going to get warm. And again, convection is basically like a big stirring rod, It's a big stirring rod that is but it's naturally done. You don't need to actually stir the air in your room to get it to flow around like this. It's just because hot air rises and cold air falls. This is just naturally going to happen. And the movement of that mass of air is what we call convection, right? In the case of the water, it's the movement of water. In the case of this is the movement of air, right? Does that make sense? That's what we call convection. Will it seem colder in the basement? Probably, yeah. Except for, of course, if you're near the radiator, right? And it would probably only be cold in the basement right when you turn it on, because eventually this process is going to stop, because all the air molecules in the room will eventually reach a constant temperature of, let's say you turn it up to 75 degrees if it's really cold. Once everything reaches 75 degrees Celsius, now there's really no more cold air anymore. But yeah. Now, is the heating system in your home this simple? I don't know. Probably not. But this is the principle of how you get warm heating all around the room, and why you don't need to sit right next to the vent to stay hot, right? That's kind of the main thing that it does. Now, have any of you heard the word convection used prior to tonight? And where did you hear it?
Yeah, for ovens.
Ovens. Is that what you're going to say too, Giselle? What were you saying?
Lava, I think.
Lava. How does it work with lava?
So like the hotter lava is on the bottom and it goes up. It basically the same movement you find here in a convection current.
And that's how that lava pushes its way to the surface and then eventually spouts out of the volcano when it gets really hot. That's a great example that I had no one has ever used before. I like that a lot. That's really good. Yeah, this could probably.
I think the same thing happens with in the ocean, right?
Yes, there are definitely convection currents in the ocean, and they can create hurricanes, right? If you think about the way a hurricane works, it's this spinning motion of the. Yep. Okay. And someone said ovens too, right? What's a convection oven? How is a convection oven different from an ordinary oven? Does anyone in here have a convection oven? Yeah, usually no one does. I feel like they're kind of old-timey things. How about this question? I bet some of you have to answer yes to this one. Does anyone here have an air fryer?
Yeah, that's the new thing.
That's the new thing, yeah, right? So I'm not certain, but I'm pretty sure an air fryer works off the same process as a convection oven does. Might be wrong about that. But a lot of my students in the Monday class seem to claim that. It definitely does something similar to a convection oven. So what a convection oven does, normal oven, the way that it works is you have some kind of hot coils on the top here, and they get really hot, and maybe you've got some coils on the bottom too, or something like that. These heat up due to however your oven works. If you've got a gas oven, I don't know how it works, but if it's an electrical oven, just electricity flows through here, and these things get really hot. And then you've got your place where you put your food, You put your food in here on a tray or whatever. You bake your lasagna or whatever you got in here, right? Now the way that the oven cooks things is actually through radiation, not through convection. Normally what happens is that rays of energy from here, basically like waves, heat up your food, okay? Now because it's radiation, if you put something reflective on the top, it will reflect the radiation back. This is why if you're cooking something like, let's say you're cooking lasagna, you might put tin foil to cover it, because that'll make it so that the radiation doesn't burn the cheese on top, right? Although you want the cheese to be kind of crusty, you don't want it to burn before the rest of the pasta in the middle is cooked, right? So what a convection oven does is it takes the radiation that's happening here and you add a fan. And what the fan does is it blows air into here, and that air circulates through. So this is air circulating through here. And it creates convection currents. And convection ovens, by comparison with normal ovens, are very, very loud because of this air that's flowing through here. And as the air flows through, though, it makes it so the food that's in the oven, supposedly, cooks very evenly. I've never used one before, but that's what people say. So who has an air fryer? Does that sound like how an air fryer works?
I think I might have a convection oven.
Oh, really?
My dad is always like, we don't need to get an air fryer, we got a convection oven.
Oh, that's so funny.
Our oven does the same thing, so it's like...
It does.
Maybe.
Yeah, it probably does, right? So my understanding of an air fryer, which is not I don't really understand it, but the goal is to basically get the moisture out of the food or something like that, and it used the flow of air to basically dry out the food. Does that sound right?
I don't know. I mean, I have an air fryer, but I just never really took the time to really examine it until now.
To see
I'm gonna actually look at it now.
What do you cook in it? What have you cooked in it before?
I mean, I've made chicken nuggets, but the thing is, when you say it sucks out the moisture, it's still moist. So
they come out kind of moist. Well, it's moist on the inside, right?
Yeah, it's moist on the inside, but on the outside it's like crispy.
Crispy, right? Yeah. So I think you can't remove the moisture from the inside probably, but you're drawing the moisture out of the flaky crust, right? To get it to be hot and crispy, right?
Yeah, I'm assuming. I'm gonna really look at my air fryer now. Now that we're bringing this up.
Oil does the same thing. I guess so. I don't really know. I used to be a fry cook. That was my first jobs. I used to be a fry cook at Chili's, and I still don't have any idea how regular frying works. My understanding of regular frying is that you batter something, right? You put it into the fryer, and I think that the batter cooks, gets hot, and let's say you're cooking like chicken strips. The chicken in the middle gets warm and heats up and gets cooked, and the oil cooks on the outside, but I think the oil can't really enter through the breading, so usually the oil kind of the outside's going to be oily, but the inside won't be oily, and it traps the moisture of the chicken in, so that when you take a bite of a properly cooked chicken tender or something like that, it's going to be really good juicy chicken on the inside, but really crispy on the outside, right? Yeah, I don't really know how oil works, to be honest. But yeah, definitely different though. The air fryer. Wait, is that the right word? Air fryer. The air fryer is less bad for you, right? Is this correct? Probably less calories because you're not coating the thing in grease. Does that seem right? You're still frying it though, and eating fried food is never going to be good for you. But it's probably a little better if it's cooked in an air fryer, I would assume. That's the appeal. Yeah, I think that's the appeal. Yeah. I should just get one, right? I should get an air fryer. Anyway, so that's convection, and we're not going to do any math because I guess we don't really have math for convection. We just kind of talk about it and understand that it's part of the heat transfer process, and it may be important, in certain systems. I guess you might be able to say that the heat flow in a computer that you use to dump the heat out of the computer, it kind of works off the same principle. Because you've got a really hot object, which is the heat sink, and then you use a fan to blow the hot air out of there. So I think it's the same concept, actually, is how a cooling system in a computer works. And if you have like a liquid cooling system, then you've got this flow of cold liquid, which is doing a similar kind of a effect. But then the liquid is actually touching the CPU, so it's more like conduction at that point. All right, so the last thing to talk about is radiation, the third and final heat transfer method. Let's make a little more room here. Okay, we didn't get to talk about this on Monday, but the last mechanism is radiation. So this is heat flow through what I would call light waves, basically, or you can call them heat waves if you want, but it's heat flow through what are called electromagnetic waves. A really great topic unto itself. This is what electromagnetic wave, we know this as light, what you call light. Heat flow through light that can occur well, kind of over a distance. I'll give you a couple examples of this. I've already given you one. A conventional oven, the coils basically heat up and then they send infrared rays into the food. They glow like red hot. That glowing red hot is indication that they're producing electromagnetic waves, and then those waves basically flow into your food, and that's how your food normally gets cooked. So your oven cooks things through radiation if it's a normal oven. A toaster would do the same thing. You know, in a toaster, if you look inside of it when it's turned on, you've got those coils that get really hot, right? And they cook your toast. So that's another example. Those red hot coils are an indication that there is some radiation occurring. And yeah, now the simplest example of this is our sun. So if you take our sun, you know, it shines and it sends energy out into space. And even though there's no matter, or very, very little matter, come on, let me pick it, please. Okay, so even though there's very little matter between the sun and the earth, okay, nonetheless, the sun's rays come in the form of waves, and they radiate energy to the earth. And that radiation is what keeps our planet warm. In fact, all of the energy on our planet can somehow be tied back to the sun, whether you're talking about fossil fuels, wind energy, obviously solar energy, that's pretty obvious, right? That comes from the sun. Even geothermal energy and hydroelectric power, those all ultimately are a result of the fact that we have this energy pumping into our planet from the sun. In the case of hydropower, the sun is what allows for the kind of like cycle of water that you need, because you need water to basically melt from the top of a mountain to flow into a stream, and then the stream, you know, you construct a dam and then you force the water to flow over some spillways, and then you harness that energy, but then that water evaporates into the clouds and then snows on the mountain, and then repeats the process over and over and over again. So ultimately, that wouldn't happen if we didn't have the sun. Same thing goes for wind power and stuff like that. The sun is the source of all of our energy on our planet, basically, and it's able to send energy just in the form of radiation to our planet. And yep, it does not require. It comes over a long distance, and there's no physical contact. So the only way this can be happening is through invisible waves of light, basically, that are heating up our planet. So that's one example. I'll give you a couple of other examples. So if you have a fire, okay, go back to our fire example. So I've got a little campfire here. I never know if this is a good example to be using with you, because I don't know how many of you have actually been camping. I don't know if it's a thing you do if you live in Los Angeles. Have a lot of you been camping before? Or no, you don't have to actually say camping. Like, have you sat next to a bonfire, basically? Or have you sat outside next to a fire? Is that an experience that a lot of you have had? Yeah.
Yes. Oh yes.
Seems like bonfire on the beach seems like it's got to be something you all have experienced at some point in your lives, right? Because that's just a really cool thing to do, right? Okay. I really enjoy fire. I was in Boy Scouts when I was a kid, and I always got into a lot of trouble for playing with fire too much. Because it's fun, you know? I mean, it's just... Fire's just fun. Regardless, let's talk about how heat transfer works with a fire. So, we said before that if you stuck a hot poker in here that we could describe conduction, right? Well, suppose that you're standing kind of far away from the fire and you're holding your hands out to keep your hands warm. As many of you have probably experienced this, you don't have to be right next to the fire to have your hands warm up, right? And that's because the fire and the logs here, the logs are actually really where it's coming from. These logs, they start to turn like red, right? They start to get really kind of like bright red, and they glow just like the inside of a toaster would glow, right? And so as you get these really hot logs down here, they start to radiate heat waves, okay? And I'm pretty sure, so that's radiation. And it's coming from those burning hot embers that, because of the fact that they're red and hot, that's an indication that in infrared radiation, that's to say, when I say infrared, that's sometimes referred to as IR. So IR is infrared. Infrared. And then the R actually stands for radiation. Have you guys heard of IR radiation before? This is like when you're watching a movie and someone puts on thermal goggles and things look like all kinds of different colors, like the spectrum of like hot and cold. Do you know what I'm talking about? Thermal vision. Allows you to kind of see in the dark and stuff like that.
Yeah.
You guys know what I'm talking about? We actually have an infrared camera on it. If you all will remind me next time we have a lab, I'll show it to you. And it's really neat because you can turn off all the lights, and you can turn on the infrared camera, and you can see everybody in the room. It's really neat. It's really cool because it picks up on hot things. Basically, anything that's hot puts out infrared radiation. So something that's glowing bright hot, like red, is dumping out a lot of radiation. So that's another example of where you can see radiation. Pretty much anytime you see like glowing embers, hot things like that, there's going to be radiation coming out of it. Okay. In fact, right now, my body is radiating energy out into the room. Not much, nothing compared to, say, the sun, for example, or hot coals in a fire or something like that, but it's happening. And like I said, I can prove it to you by shining an IR camera on you and showing you that there are heat waves. So sometimes people refer to these as heat waves. I'm not going to write that down because it's not very scientific. It's infrared radiation, that's what we call it, but anyway. Okay, does anyone have any questions or comments? If you like to understand kind of what I mean when I use the word radiation. Okay. So how do we quantify it? Again, this is not something that we can derive. So what I did was I just took the entire thing out of the textbook, so you could have it here in the notes, and blah 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 blah. Here's the equation. Here's the equation. So heat current for radiation depends on the following things. It depends on the area of the emitting surface. So let's think about the sun. What would the area of the sun be? You'd have to take a cross-sectional area of the sun, kind of like this. You'd basically slice the sun down like this, and you say the sun has a cross-sectional area A, which, would be pi r squared, where the radius of the sun is the thing, right? So that's your A. I know it's a globe, or it's a sphere, but when we talk about this, we need an area. And then you have emissivity. So a dimensionless number between 0 and 1. E is a ratio of the rate of radiation from a particular surface to the rate of radiation from an equal area of an ideal radiating surface at the same temperature. That's a lot to take in. But all you need to know is this number from between 0 and 1, and any given problem, they're gonna tell you what it is. An ideal radiating surface, you're gonna learn in physics. I'll tell you what an ideal radiating surface is. A burning piece of coal is nearly an ideal radiating surface. The sun also, or the sun. And for these objects, the value of the emissivity would be equal to 1. Okay? So if I have an object that has an emissivity of 0.5, that means its rate of energy emission is about half as strong as the sun or burning coal. These things you're going to learn, maybe you've heard this before. I'm sure some of you might have taken 1D, I don't know. But if you do, you'll talk about something that's called black body radiation. And black body radiation is the radiation from an ideal radiating surface. So you'll see this concept come up later. And when you take physics 1D, you'll probably see this equation at some point, and it's probably going to be when you start talking about Max Planck and his discoveries regarding the radiation from black bodies, one of the first pieces of evidence that classical physics has some problems. Really, really exciting. All comes from this. So the heat current depends on the area of the surface. It depends on emissivity. It depends on sigma. Sigma is the Stefan-Boltzmann constant. It is effectively a conversion factor, okay? It's like the G that shows up in the gravity equations, the big G. It's also like, kind of like, no, not the spring constant. Wait, is that, if you've taken only 1A, you probably only have big G as the big constant that you've learned, right? You don't learn any other constants in physics 1A, do you? And by constants, I mean like, you learn about spring constants, but a spring constant is different for different springs. This is a constant that's the same for everything. It's always this value. And if you'll remember the force of gravity from physics 1A, which is like big G times m1 times m2 divided by little r squared, where big G is equal to, nope, can't write it there. Running out of space. Where big G is equal to this. You guys remember this?
Yeah.
So this is really just a conversion factor. That's all it is. Because normally we measure force as mass times acceleration, or mass times gravity, or something like that, right? But the units of this would obviously be different, because this is kilogram times kilogram divided by meter squared, so you need to have something that turns it into newtons, and that's what this is. Well, the Stefan-Boltzmann constant is exactly the same. It just takes all this stuff and outputs watts. That's all that it really does. It's something you would measure, okay? Has been measured out to a large degree of accuracy right here. But that'll be the same in any given problem. And then also depends on the temperature of the surface, measured an absolute temperature, that means kelvins. So you take area times emissivity times sigma times T to the fourth. And that's it. These problems are generally kind of easy because you just kind of plug the numbers in, you know? But there we go. Any questions? We'll do some problems. It'll make more sense if we do problems. Okay, now the other possibility that you can have, and this might be the more common one, is if you want to find the net heat radiation of an object, and you have an object that is surrounded, then what you need to do is to find the net flow, you find you do all this stuff, and you multiply by 2 to the fourth, and then you subtract the absolute temperature of the surface and its surroundings. So TS is the temperature of the surroundings. So the idea would be, so suppose that I've got some object here. Maybe it's a piece of coal, and maybe it's burning, so it's hot, right? And it's going to have some cross-sectional area A, it's going to have some temperature T, and then you would say, but also all around it here, you've got a temperature of S. So for example, if the burning coal was at a temperature of, I don't know what burning coal is going to be at, let's say 500 Kelvin for T, and TS is equal to, let's say, well, the surrounding temperature would be like room temperature, which might be like 293 K, right? So this could be equal to T, the temperature of your object, and the temperature of surroundings might be 293 K. Well, then you can figure out the rate at which that coal actually emits energy into the environment. And it's going to get bigger the smaller the value of the surroundings is. And it's also going to get bigger the hotter the coal gets, which should make sense. The hotter the coal is, the more it's going to dump energy into its surroundings. But if it's really hot outside, it can't really dump energy into its surroundings, so you need to subtract that off. And then it says here that it's positive if the heat flows out. It'll be negative if the heat flows in. How did they figure out that it was T to the fourth? They did a bunch of measurements. That's why we call this an empirical law, because they just had to take a bunch of measurements. They had to design some kind of experiment that could measure heat current. That sounds really hard. And then they had to somehow figure the relationship between the heat current and the temperature and all these other things too. Must have been pretty hard, especially when something like emissivity is something that's got to be very difficult to even estimate. And that's probably what they had to do. They probably had to estimate it. In fact, probably what they did, I'd love to go back and look at what they did, but I would guess something about what they did was they would have used something like coal or pitch, which they knew was effectively emissivity 1, and then they took a fixed value of area and probably tried different areas to see that, okay, yeah, it is dependent on the area, and they probably just took a lot of data and they fit this side to this side by using what you all have to do in the recent lab, which is you do a log-log plot, right? If your goal is to figure out what this power is right here, that's what log-log plots are for, right? Because if you take the log of both sides, the 4 comes down in front and becomes the slope of your log-log plot. So that's a nice kind of application of what we've been learning in class or in the labs. Those of you that have done that lab, I know half of you may not. Well, actually, in this class, most people have already done it, I think. All right. Any questions before we move into solving some problems? We can probably do like one. We can probably do more than one if you guys don't mind if I go really fast, because these are pretty short. So we've got the absolute one here. Let me write the equation down. So it's AE sigma T4. That's equal to the heat current. So heat transfer by radiation. We have a thin square steel plate, 10 centimeters on a side, is heated in a blacksmith's forge up to 80 degrees Celsius. If the emissivity is 0.6, what is the total rate of energy radiation from the plate? Okay. So it's telling us that the emissivity is 0.6. It's telling us that it's 10 centimeters on a side, which means its area is going to be equal to 0.1 meters whole squared. So the area is going to be equal to 0.01 meters squared. It's also telling us that the temperature is 800, but for us, the temperature needs to be 800 degrees Celsius plus 273. We'll just use 273. I never know what the proper way to write this is, but the temperature in Kelvin is going to be that. 800 plus 273 would be 1073 Kelvin. And then I think that's all we need, right? And then we need sigma, which we can't see. So we'll scroll up just a little bit here. There's sigma. If we plug everything in, we're going to get H is equal to A, which is 0.01 meters squared, multiplied by E, which was 0.6. Sigma, which is, we'll just write this as 5.67 times 10 to the negative 8. Hey, you all tell me, those of you that have taken chemistry before, have you seen the name Boltzmann before? Oh my god, they did it again. Look at this. I hope that makes you mad. Ugh, it's so maddening. Kelvin to the 4th goes in the denominator, even though for them it doesn't. Alright. Oh, that, and then we also have to multiply by temperature to the 4th power. Kind of running out of room here, but I think I can fit in here. 1073 Kelvin to the 4th power. And then what I'll do to... we'll make this a different color. Red for heat. Shift it over just a little bit so we can distinguish from that, and then I'll fix that 4. I got turned into a, who knows, like a 9 or something. I need to start writing my 4s like that. That way it doesn't matter. Okay, so, do all that, what do you get? Seems like it should be a really big number, but we're going to have to multiply by 10 to the negative 8, so that's going to suppress the value. We don't use the 4th power very much, do we, in physics? It's usually squared or, you know, like maybe cubed sometimes. If you're talking about volume, you don't see the 4th power very much. Kind of makes you wonder why it has the 4th power, doesn't it? You don't wonder that? Why is it the 4th power and not the 3rd power, the 5th power, the 2nd power? You know what I mean? Why is it the 4th power? That's really weird, right? Really weird. It's almost like there's something else going on. Anyway, I got 451. Did I do it wrong?
I got 451 too.
Okay, if you got 4.51, maybe it's probably something here that I've written that you can't read. This is to the -8, by the way. If you thought it was like -6. I don't know. That might be one way you got that answer. Or maybe here. That might be it. Maybe you didn't multiply by... Wait, that wouldn't make any sense. I don't know. Anyway, 451. And that is in watts, right? Because meters squared is going to cancel out with meters squared. Kelvin, this is Kelvin, to the 4th power is going to cancel out with that Kelvin, and you're just left with watts. So that's the heat flow from our... And what is this? It's a piece of metal that's basically just been superheated, and now it's radiating out energy. Does that make sense? I could have drawn a picture, right? I probably should have drawn a picture. Got this piece of metal. It's really hot, and it's sending out energy. Okay, does it make sense? Pretty easy, right?
Pretty easy.
Okay. Now, next thing. Radiation from the human body. This is the one where we're going to use the second equation here. So let's write it down. The second equation is basically H is equal to AE sigma. And then here we put the temperature of the object to the 4th power minus the temperature of the surroundings. It's a long word, to the 4th power. You know what else goes as the 4th power? The wavelength of light that is absorbed by the air. It's also a 4th power thing. It's probably related to this. Anyway. It's one of the ways you can describe why the sky's blue. All right, so that's our equation. What's the problem? What is the total rate of energy, a rate of radiation of energy from a human body with a total surface area of 1.2 meters squared? I wonder if that's like how big of a person that is. And a surface temperature of 30 degrees Celsius, 303 Kelvin. So we know the temperature of the body is 303 Kelvin, right? So we've got a person, and they're radiating out heat, and the temperature of the person is this. But their surroundings have a temperature at 20 degrees Celsius. 20 plus 273 will be 293 Kelvin. What is the net rate of heat? So they call this one H net. What is the net rate of radiative heat loss from the body? The emissivity of the human body is very close to unity, irrespective of skin pigmentation. Is it really? So very close to unity means we are going to use E equal to 1. I have a hard time believing that, but hey. You know, it's a science textbook. What's the odds that it's wrong? Anyway. All right, H net is going to be equal to, then we just take the area of 1.2 meters squared. We multiply by the emissivity, which we're taking to be equal to 1. It said very close to 1. We could use 0.9. I'm just going to use 1. We put sigma in here, which was like, what, 5.67 times 10 to the minus 8 watts over meters squared Kelvin to the 4th. I'll check to see if that's right. I could be wrong. Yep, 5.67 times 10 to the negative 8. All right, and then multiply by... Kind of run out of room, so let's shift this over a little bit. Temperature to the 4th for the object, which was 303. Now you'll notice in this case that the temperature difference is very small, right? It's very small. However, when you raise something to the 4th power, it doesn't matter if it's only 10 Kelvin difference, because 303 to the 4th power is much, much bigger than 293 to the 4th power. I think it is, at least. Let's look. So 303 to the 4th power is, God, it's a huge number. This is 8.4 times 10 to the 9, so it's 8.4 million. I'm just going to write it out like this. And then that's minus 293 to the 4th power, which is only 7.3. Okay, yeah, about 7.4 times 10 to the 9. So look, the difference is actually 1 times 10 to the 8. Isn't that crazy? Even though they're only 10 degrees apart, when you put it to the 4th power, the difference is, what is that? 100 million? It's kind of crazy. Anyway, that's just, I don't know, I like numbers. Okay, so what do you get if you calculate this out? So you're going to get 1.2 times 1 times 5.67 times 10 to the negative 8, and then times this temperature difference, so 303 raised to the 4th power, minus 293 raised to the 4th power. I got 72. Watts. This, I think, is about twice as big as the heat flow into the cooler that we got earlier, right? The heat flow into the cooler was like 35, right? 36, something like that. This is just about double. That means that the heat flow out of your body is about half as much as the heat flow out of styrofoam, or the heat flow into styrofoam. Just kind of interesting to think about. So, of course, this means that in order for us to not freeze, right, we have to generate enough energy to offset this, right? Oh my God, what just happened? You know what I mean? In order for us to not freeze, we have to generate enough energy internally for this to not be completely offset. We have to actually generate more energy than this, or at least as much. Otherwise, our temperature will start to drop, right? Well, anyone have any questions? Kind of out of time. Thanks everyone for showing up tonight. I know that showing up after an exam is, it's very easy to just skip the next class, but it's often important to keep showing up, even if you're exhausted from taking a bunch of exams and stuff, which I'm sure you all are. So thanks for sticking it out. And I just want to remind you that the group of people that have not yet done F5, you're going to be doing F5 on Monday night. So do you all know who you are? Anyway, I'll see you all Monday. It's a pretty fun lab. You're going to be dropping little balls down through glycerin and calculating terminal velocity. And then you're going to be, So any questions before we go? Basically, if you haven't done F5 yet, show up on Monday, right? I'll try to put up a reminder or something later in the week. I also, I changed the due date for the heat transfer homework to, I think, Sunday or something like that. Just so you have plenty of time. And like I said, I'll do my best to try to get back that exam to you, hopefully on Monday night. If you show up, I mean, if you're a student that shows up Monday night, I'll try to have the exam graded for you. And then those of you that go on the other night, I'll get it back to you the next week. They take a long time to grade, just so you all know. And it takes me about, for a 30 student class, I spend about 15 minutes per exam. So that's it takes a long time. It takes a long time. I graded a total of 15 exams today, and it took me 3 hours. It's just it takes so long. But I'll get them back to you, I promise. And I'll try to do so in a... Good night, Professor. Take your time. More time. It does. That's right, Ryan. That's right. If I grade it fast, it's just going to be like, this is wrong, that's wrong. Turn it back to you, right? But if I take time, then I can really look at what you've done, and that's what I want to do. I want to give you as much credit as I possibly can. I'll do my best to give you a bunch of partial credit, because I'm sure that test was really hard. Honestly, that was the first 1B exam that I've ever written. So, there's some error correction that goes on where if I made it too hard, I'll know next time to make things a little easier, and maybe I did. But we'll see. So, hope you all have a good night. Go Dodgers. Hope you guys have a good one. I'll see you next week on Monday, okay? Stop streaming. Oh, I need to close the...